Alright, this video is on covalent bonding and the introduction to something called orbital overlap. And we're going to connect this idea a little bit with VSEPR and then with the formation of a molecule. And this is kind of the lead into the next section on something called hybrid orbitals. So the first thing we talk about in this section is that while VSEPR predicts molecule geometry, there are a couple shortcomings. And the first big shortcoming is that while it predicts the molecular shape, it does not account for why and even how bonds exist between atoms. So this idea of orbital overlap is a little bit of an explanation into why bonds exist. Okay, so it's kind of the combination, I guess, of two big ideas. Atomic orbitals. So that's your S, your P, your D, your F, right? And Lewis structures. And those two ideas together give us a name called valence bond theory. And that's what we're discussing next. So let's see, we know that Lewis structures show us that atoms share electrons, and that there's this what we're going to refer to as electron density between the two nuclei of the atoms. And what valence bond theory discusses is kind of the merging of atomic, my goodness, I don't know why I keep doing that. The merging of atomic orbitals. Okay, so what we're gonna start talking about is that orbitals will share a region of space, should be a P, and we call it orbital overlap. Okay, so a simple idea here would be like the hydrogen atom that has a nucleus, okay, plus a second hydrogen atom with a second nucleus. If we bring those two atoms close together, what we get is an overlap of those. In this case, it would be like the s orbital, okay? So it would look something like there's your first nuclei, there's your second nuclei, and it looks like a Venn diagram. But there's this space right here where the s orbitals have overlapped. Okay, and that is the covalent bond. So maybe you've never really thought of it like that before. But you could also have, so like in this case, we were talking about an S and an S orbital, but maybe you even have like, I don't know, in a different example, you know, a 2p X, right? And another 2p X. And if you bring them together, I shouldn't have drawn it like that. If you bring them together, there's my first P, and then here's my second P, okay, and there's that overlap region. Okay, so this idea of valence bond theory deals with overlap, and kind of the takeaway point, or the big idea in this case, is that there's always an optimal distance for overlap. Okay, so meaning there can be situations where the overlap is too much There can be situations where the overlap is too little, and there can be situations where it's perfect. So like when I teach this, and when I've taught this prior, it always kind of comes up like Goldilocks and the Three Bears, right? Like the porridge that's too hot, the one that's too cold, and the one that's just right. That's what this reminds students of, in the fact that there's always kind of a sweet spot, so to speak. There's always a porridge that is exactly the right temperature. And although that's really silly, it's kind of a good comparison, I guess, in your mind. So this is a graph, and this is an extremely important graph. You'll see this it's been on the AP test before. It appears a lot, and this is the reason why we have molecule formation. So if you look at what this graph is, it's a graph of energy, okay, versus something called the internuclear distance, which is basically the distance between the two nuclei, okay? So in this case, it's the formation of H2, which is, of course, formed from two hydrogens. So when we look at the hydrogens being too close together, and think about it, too close, the internuclear distance is very small. So the nuclei are too close, they're kind of on top of each other. And look at the energy. It's very high in the in the positive value, okay? There's too much energy associated with this. What's going on up there is we have too much repulsion. So think about it. We have two types of repulsion that would be happening. We have electron and electron repulsion, but we also have the nuclei repulsion, or the proton repulsion, right? So the protons don't like each other either. So in this case, we have this, even though we have attraction, because see, that's the issue. Some students will say, well, there's still attraction between the protons and the electrons. Oh, absolutely. But the issue with this is the repulsion is overriding that. There's way too much repulsion when they're too close. Now, the opposite kind of discussion to that is what happens when they're too far apart. So again, look at your internuclear distance. It's really high. Okay, that means your atoms are way far apart. They're actually like separate molecules. I should say atoms, sorry, because they're hydrogens. And if you look at the energy, it's an energy value of 0, which means they're basically behaving as separate atoms. Okay, there really is no bond here to speak of. There's really no bond because the atoms are so far apart. So then we get the sweet spot, so to speak, which is the perfect distance between the two hydrogen atoms. That distance, okay, is something that can be measured, and it's referred to as a bond length. And in this case, it's 74 picometers, but nobody needs to know that. But that is the bond length of the H2 molecule, okay? And so what's happening at the bottom of this well is the distance is just right, because at this point the attraction of the protons and the electrons outweighs the repulsions. So remember, we said, in both instances, the too close and the perfect, we have attraction and we have repulsion. It's just when they're too close, repulsion wins. And when they're just right, the attraction wins. Okay, so that's what this picture shows you. And the biggest takeaway that we can probably say is at this bond length, at this perfect situation, look at the energy value. The energy value is negative, which means energy is released. And that's why hydrogen atoms prefer to covalently bond as a molecule, because they release energy. And that's a better place to be than in a high energy situation. And that's where we talked, back in thermo, that all bonds require energy to be broken, but all bonds release energy when they're formed. And this is a perfect example. It's just an example in graphical